Welcome to the EC Game Changer online seminars. It's the 89th online seminars. We started the series during the COVID to keep the community together and to serve the community with something that you cannot do in person. So we started this Game Changer seminars now more than 2 years ago. It was very successful. And so we still keep the seminar at life, living. Even now, people are turning back to Bern, to EC, to work together, to meet together, and to do science. So, of course, all the people attending now the seminar, you're all welcome to visit Bern and to apply for your projects and to come to EC. Today, we're happy that Jeremy Schnittman accepted our invitation to give a talk on life on Miller's planet, the habitability zone around supermassive black holes. Jeremy Schnittman joined the astrophysics science division at NASA Goddard in 2010, following postdoctoral fellowship at the University of Maryland and Johns Hopkins University. His research interest is quite broad. He's for sure doing theories and computational modeling of black holes, accretion flow, X-ray polarimetry, black hole binaries, gravitational wave sources, and gravitational microlensing, dark matter annihilation, and planetary dynamics, resonance dynamic, and exoplanet atmospheres. I like the last sentence that he has been described as a general purpose astrophysics theorist, which he regards as quite a compliment, and it's nice to have, of course, scientists being so broad in the interest and publishing actually whatever he's publishing at a high level. So Jeremy, thank you for accepting our invitation, and of course we are all look very much forward to your talk. So okay. Just for the people, just sorry, 1 second now. You can ask your question always, or if you have any question, you can write them down in the chat. Or at the end of the talk, you can raise your hand and ask your question. And so it means you will be unmuted, or you can always ask your question also at the end directly in the chat. Jeremy, okay. The screen, it's yours.
All right. Thank you, Marcio. Thank you so much for the invitation. I only wish I wish I could be there in person. It sounds like a wonderful place, and hopefully I will be able to come visit in person in the future. So we're going to talk about this kind of wild idea, right? This idea of living on planets that orbit supermassive black holes. Of course, it's based on this this movie that came out now almost 10 years ago. I think it came out in 2014, the Interstellar movie. And of course, that's the plot line of that movie, of exploring planets around black holes. In particular, one of the planets, called Miller's planet, is the one that's closest to the black hole. So hence the title of the talk. So even though it really is based on science fiction and obviously all fictional, we've decided to kind of take it where it will go and explore some very real physics and astrophysics ideas that come out of it, and then that I think are worth thinking about, even if they're not necessarily going to affect our everyday life or our actual search for life on extrasolar planets. So with that in mind, we'll start with a little bit of acknowledgements. Where does some of these ideas come from? So obviously a lot of the influence is coming from the physics and the creativity and original thoughts of Kip Thorne, who is the chief science advisor for this movie. And probably many of you know him and his work. Maybe less well known in this community is my former boss and a dear friend, Piers Sellers, who was an astronaut here at NASA. Unfortunately, he passed away right at the end of 2016. But Piers was there are basically two types of astronauts. There are the fighter pilots and the scientists. And Piers was a pilot, but he was also primarily a scientist, and he worked at Goddard for many years. He was an earth scientist who was just insatiably curious about all sorts of different types of science, including black holes. And under his direction, we actually started a large interdisciplinary effort here at Goddard to apply some of the things we know about, for example, earth science and atmospheric science that we learned from the kind of the earth science division, and apply it now to what we're learning so rapidly and so much information pouring in on a daily basis about exoplanets. So now we've actually, this organization has grown to probably at least 50 people now at Goddard are involved in this operation at some level. And it has now been named after peers. It's called SEEC, the Sellers Exoplanet Environments Collaboration, or Center, I think is the C. So they organize a lot of meetings and collaborations and funding. So you hopefully will hear about them in the future. So here's the movie poster, the Interstellar, the Christopher Nolan movie. Maybe has a date without a year. I should have checked, but I'm like 90% sure it was 2014. And then you can even see, if you zoom into the credits down below, there's Kip Thorne, listed as an executive producer. He's really the science advisor behind the whole movie, even to the point where he wrote a book about the science of Interstellar, which is a great book. I think I do have it right here. Okay, so now with working half home and half from the office, it's hard to remember which books I've left where. But it's a fun book, and one of the things I like the best about it, aside from the fact that it's great writing and Kip's a great writer and great science, they go through the book, and you can see each little section right at the top of the section kind of gives a little ranking about just how realistic or speculative each part of each section of the science in the book is. So that's helpful for a reader or a viewer of the movie to say, well, does that really happen? Does that really happen? So we will touch on that also throughout this talk, and try to focus on the things that we are fairly confident are real science and not just complete science fiction. Okay, so like I said, the movie came out quite a few years ago. So in case people on the talk either have not seen the movie or can't quite remember what happened, we're going to just show a short clip. All I can say is the NASA lawyers here, of which we have plenty, said that this is what we call in America, at least, fair use copyright. So this hopefully should not cause any trouble with the copyright. I don't know if we post this on YouTube later, it might get blacked out, but hopefully you can see it and hear it for now, because this is the meeting in the movie where they kind of explain what the whole point of exploring these planets is. So we'll watch this for a minute and then discuss. Okay, so I realized that Matthew McConaughey does kind of mumble, so I hope people were able to hear that. So the thing I really want to take away from this is that both in sci-fi, when you're going out and exploring the universe and looking for potentially habitable worlds, you take a very similar approach to the way that we take, for example, at NASA when planning missions, right? There's this kind of wedding cake structure of a lot of our searches. You started with the base of a big, broad search, right? So, for example, a mission like TESS, which is searching right now for, surveying almost the entire sky, looking for exoplanet transits, right? And looking at literally millions or even billions of stars, calculating lots and lots of little light curves, very rudimentary data about many signals. So it's like they said in the movie clip, right? They're just getting very like snippets of binary data coming back through the wormhole, trying to explore all these different worlds. So similar to us too, we take this huge survey where you have just a little bit of data on a huge number of potential planets, and then you kind of do a triage where you take your best candidates from there. You will follow them up with, say, for example, ground-based radial velocity surveys to get better information about the planet's orbits and masses. And then from there, you kind of narrow it down to an even smaller number of candidates. And then at that point, maybe you'll start pointing Hubble or JWST at these planets to get transit spectroscopy. And you really just keep narrowing it down in investing essentially the bigger and more expensive resources at the smaller and smaller, more promising targets. So from that point of view, really the movie is very reflective of our strategy in real life of exploring exoplanets. And then ultimately also, like in the movie, they kind of narrow it down to these 12 targets, and they send probes there, and they send probes and people to get the in situ measurements. And same too with our study of exoplanets in the solar system. We can get great spectra now from JWST, but it's really nothing at all compared to what you can get from either an orbiter or, of course, a lander or a rover on Mars, on Titan, on the nearby planets. Can obviously give so much more information. And even that pales in comparison to getting like an actual person, scientist on the surface of a planet, taking in situ measurements and getting, organics and all of that sort of information is really the ultimate in exploration. So here's just a plot, that probably needs to be updated, but just again, showing the sheer variety and panoply of different exoplanets we see. Where we plot, it's very common method of plotting them, where the x-axis is the semi-major axis, the distance from their host star, and then the mass of the planet is on the y-axis. And then the color in this plot, the color is the effective temperature of these planets. So, sorry, the effective temperature of the star, right? We're talking 5,000-6,000 degree stars. Again, we can look at a lot of different dimensions of this plot: eccentricity, planetary radius as instead of mass. There's a lot of different information, obviously, that we want to get. But you'll notice, at least with this data, let's look at the Earth type, Earth-like, and you see, nope, there's one AU, and here's one Earth mass. Still pretty sparse. This region of the purely Earth-like exoplanets. So either we just have to keep looking and coming up with better and better more sensitive instruments, or I think another takeaway from a plot like this is you can look at Earth-like planets, but not on Earth-like orbits. So these are the Earth-size planets, all of these guys, but on the orbits that are much closer to their stars. Of course, those are much easier to detect with transit observations. And some of these are not sun-like stars, but they're cooler, like M-dwarf stars, in which case, even though you're 10 times closer to the host star, the net flux coming from the star is much smaller, for example, if they are an M-dwarf. And that's kind of shown here, where we're now plotting, again, distance, but now instead of the planet's mass, we're plotting the star's mass on the y-axis. So, and then this orange stripe is kind of a rough estimate of where this habitable zone is, where we think that you could have kind of Earth-type life on the surface of a Earth-ish planet, some sort of a rocky planet. So, as you see, these letters, right, these correspond to the different stellar types: higher, larger, and hotter and brighter, going down to smaller and fainter and dimmer. So it makes sense that for the fainter stars, like these M stars, the habitable zone is closer and closer to the star because it's, you can get closer and still be at that nice room temperature where water can exist on the planet. And then here's just for reference, here's the solar system where Earth is smack in the middle of the habitable zone, and Venus and Mars are a little bit inside or a little bit outside, right? Venus is a bit too hot, Mars is a bit too cold, at least now. Another point of this plot that I wanted to point out is this dotted dashed line, right? Which is we call the tidal locking radius, because as you get closer and closer to the star, especially these faint stars where they're cool, so you can afford to get closer, even though they're much cooler, they're not that much less massive, 10-20% of the mass of the sun. So they still have significant gravitational forces, and those can lock the planet in place, just like the moon is locked in tidal locking, and it doesn't, always same size faces the Earth. So too, the same size of these planets faces their host star. Anything inside of this dashed line, even though they're still habitable, they're close enough to the star to get locked in place. So you always have a day side and a night side of these planets. And that in turn is interesting. I won't get into the details here, but essentially when you have a day side, it's not day and sunny all the time, but in fact, a lot of these, we expect them to be very cloudy. In the lower right here, this is the cloud coverage done from some simulations of different planets. In fact, with a Earth climate type simulation code, again, this we were talking before about bringing in information from Earth science onto exoplanet science. And you see that you can get this is labeled on top with the total energy coming from the star. You can get a lot more energy coming from the star and still end up at the same temperature, because you can build up this huge cloud coverage that kind of acts as a solar umbrella, essentially, to block the direct sunlight and yet still keep the planet at a reasonable temperature. So that's an interesting aside, but I think really what we're going to be mostly focused on for the rest of the talk is when we talk about the habitable zone, whether it's inside the tidal locking radius or outside, we're going to kind of use that as a little bit of wiggle room to allow this range of about 120 to 750 watts per meter squared on the surface of the planet. And if we're in that comfort zone, we'll call that habitable. That's where liquid water can exist on the surface of the planet. So when we talk about, right, here's the plot for tidal radius as a function of the stellar mass. Now we're going to switch over to start talking about black holes. This is what it looks like for a central black hole that's 10 to the 8, 10 to the 9 times the mass of the sun. So all that happens is the tidal locking radius simply scales further and further away. As you can see, even out at 100 AU, well beyond the orbit of Pluto, if you're going around a black hole, you're still going to be tidally locked. And in fact, instead of AU, which is obviously very solar system centric unit, for the rest of this talk, we're also going to switch over to black hole language. So instead of talking about AU, we're going to talk about what we call a gravitational radius, which is essentially the characteristic size of the black hole. Not always exactly the event horizon, but it's kind of like on the order of the event horizon. So one gravitational radius is like the radius of the black hole. And it's convenient for these numbers that we picked, actually, that 10 to the 8 solar masses, one gravitational radius is 1/8 AU. So then we can kind of scale it, flip it over from AU now to RG. the gravitational radius, the gravitational constant times the mass of the object divided by c squared. And because that flips, now this line essentially flips, so that as you go to higher masses, you actually have to get closer to the black hole in the units of the black hole radius before you get tidally locked. This is kind of an interesting feature of black holes, is that smaller black holes essentially have stronger tides, because you can kind of think of them, they're like more curvy. So when you get close to them, you can kind of feel that curvature more. Whereas you come to a big black hole, like the horizon just looks like the horizon on the ocean, big and flat. You don't really feel the curvature as much. Okay, so again, this is the unit for gravitational radii, and we're going to be focusing on this a lot. In fact, a lot of the times we're going to be focusing so close to the event horizon, we'll even switch these this x-axis essentially to be measured in units of gravitational radii, not from the center, the singularity, but from the horizon. So like 1 gravitational radius, 1.0001 gravitational radii, etc. And we'll see that soon. Here is just a nice little demonstration of that tidal locking. I mentioned, right, we know the moon is tidally locked and it kind of librates and wiggles throughout its orbit, but we essentially always see the same side of the moon throughout the month. And of course, everybody on this call probably knows that, right, there's no such thing as a dark side and a light side. There's the near side and the far side. That's not that relevant, but I like this movie, so I put it in there. Okay, so now we're talking about the black holes, and we're talking about the habitable zone. So now we've talked about the energy source, right? Where is the energy source? For a star, it's obvious. The energy source is the star. The light's coming from the star, heating up the planet. For a black hole, the standard energy source would be something like an accretion disk, right? You get gas orbiting around the black hole. Here's the artist's impression. The gas swirls around. As it gets closer to the black hole, it gets heated up higher and higher. It gets higher in temperatures, and you get more flux. For most astronomical black holes, that flux is coming out in either ultraviolet or X-ray at very high temperatures, X-ray light, and that's how we typically detect and study black holes. So here's the artist impression. Here is the astrophysicist's impression, my computer simulation of what the black hole looks like. Now this is that very characteristic shape of the accretion disk that is in the movie poster and kind of pops up all over the internet these days. Here's just a simulation I made of this turbulent gas orbiting around the black hole, which we're looking at the accretion disk now kind of edge on. Oh, and now we're going to flip it up to get the full effect here of that gravitational lensing as you rotate that accretion disk around the black hole. And you can see again both the gravitational lensing, and the other notable feature here is, right, you see the light coming from one side of the accretion disk is brighter than the other because it's coming towards us. You get that Doppler effect. So the light, is brighter. Light coming towards you is brighter, and of course the light orbiting around a black hole is going at some good chunk of the speed of light. So that Doppler effect is significant. This is actually, as an interesting aside, this is an effect they did not include when simulating the images in the movie Interstellar, and Kip even describes it in the book as to why, because he knows that you have to include that. It's an inevitable result of the laws of physics. But Christopher Nolan, the director, he decided that it was a little too confusing, right? There's it's already kind of mind-boggling to think of what things look like orbiting black holes. So to add that extra piece of information would be too complicated. So again, it's an example of where Kip describes the real physics in the book and then explains the justification for leaving it out. Okay, so here's just a standard calculation from Novikov and Thorne. Again, Kip even showing his face in all aspects of this work. So again, here now we're plotting this slightly different logarithmic scale of radius. This is the number of gravitational radii essentially outside of the horizon. So the horizon would be at 1. So this is r minus 1. All right. So as you get closer and closer, this would go to 0 at the horizon. And then farther away, it's just kind of approaches the standard distance. And what we've plotted here is the temperature as you go to different black hole spins, right? The black hole itself is spinning just like pretty much everything in the universe is spinning. Stars are spinning, planets are spinning, galaxies are spinning. So we expect black holes are also spinning. And as black holes spin up faster and faster, the orbits around them can get closer and closer to the horizon before plunging in. So that's why you see these temperature curves as the spin, which is just a number between 0 and 1. As the spin gets higher and higher, closer to 1, the temperature gets hotter and hotter because it's getting closer and closer to the event horizon. And the black hole in Interstellar is spinning at almost exactly 1. So we're going to see this temperature of the accretion disk getting all the way up to, well, in this case, it would have been something like 200,000 degrees Kelvin, which is very hot. Our sun is at only 5,000 degrees Kelvin. So this is 20 times hotter than the sun, which makes it actually the brightness goes like temperature to the 4th. So it's many orders of magnitude brighter than the sun. So in order to be habitable, you have to be orders of magnitude even farther away, right? So you don't want to be like this, right? Here's the kind of the movie poster. You don't want your planet to be like right there next to the event horizon on top of the accretion disk, or it would be, millions of times too hot to survive. So here's actually kind of reminiscent of that first plot where we showed the habitable zone around different types of stars. Here's now the habitable zone around the 10 to the 8th solar mass black hole with these radii. But here now, the y-axis is not the mass of the black hole. What it is the accretion rate, how much of gas is actually going through this disk. Because in this plot, this was when you kind of have the maximum amount of gas. The more gas you have coming through, the more energy is released, so the hotter it is. And in fact, like I said, it's too hot. 200,000 degrees is too hot. So the way you dial that temperature down closer to, say, 5,000 degrees, like the sun, is by dialing down that accretion rate. In fact, you have to dial it down quite a lot, right? Look at this, 10 to the minus 10 times the standard, the kind of the standard quasar accretion rate. If you can get 10 billion times less gas, so 10 billion times less energy released, then you can start talking about a habitable zone out here in in a reasonable spot around the black hole, 10, 100 gravitational radii away. But as you get too close, you kind of run out of options here. This is just a kind of a plot to show that whether the black hole is above the disk or even embedded in the disk and kind of in a warm bath surrounded by the gas, it doesn't really make too much of a difference. So the only way you can ever really survive if the black hole is accreting, right? And this is important to know, not all black holes are accreting. The one in the movie looks like it's accreting, right? All of the pictures show a big accretion disk. That, again, because it's a movie, they want to make it in the visible light. So corresponds to something like solar temperature, but that would be pushing the planets way, way, way out here to hundreds or thousands of gravitational radii, which is not what they actually showed in the it's not what they actually showed in the movie. And think, yeah, okay. So this is just, you know what, I'm just checking the time, and in the interest of time, I'm going to skip that. That's just kind of a side core point. But we want to get into another important part of the plot here. So this is another one of my favorite parts of the movie, because, you know, relativity, folks, right? Relativity effects of time dilation, how time behaves differently closer and closer to a black hole, actually ends up driving one of the major plot points of the whole movie, right? Like you said, an hour on the surface of the planet, of this Miller's planet that they're looking to explore, is 7 years back on Earth. So that's a 50,000 times time dilation. So if they go down to explore the planet for even just 1 hour and then come back, everyone in the whole story that they know is going to be 7 years older. And then, of course, so that affects their decisions whether they should, you know, spend that time exploring if their ultimate goal is to go back and save people on Earth. So what this means from a physics point of view is also really interesting, right? Here's a plot now of that time dilation as you get closer and closer to the black hole. So whether we're talking about the kind of the spin of the black hole, right? You have to get higher spin to get closer and closer. And then also kind of where that distance is located. So this is what we're just marked on this plot. It has to be extremely, extremely close to that number, right? The spin up to what we call the critical value of number 1. And the radius here, I'm plotting the radius as a distance from the horizon, is, you can see, you know, 10 to the -4, 10 to the -5 units outside of the horizon. And then this is the time dilation. Again, up here, you can see about 50 or 60,000 times time dilation. That's that 1 hour to 7 years. So the reason this is so important from a physics point of view is that, picture yourself, right? One person's going to kind of stay back on the mothership, and one person's going to go on a little scout landing ship down to the surface. And that time difference, even between the mothership and the planet surface, is that factor of 60,000. So they could communicate maybe, but that time dilation is going to start acting up, right? Let's say they're communicating with Morse code, right? So kind of shining and clicking a laser pointer or something, a radio beam from the one ship to the other, clicking it, say, you know, 1 time per second. Well, the person on the little scout ship going down to the planet, as his time slows down, the rest of the universe, like all of their time kind of adds up. So picture all of those laser pointer clicks over 7 years of messages sent down, landing on this person's head on the planet in 1 hour. So instead of going, you know, once per second, you're getting something like 60,000 clicks per second. So of course we wouldn't be able to hear that or understand it or anything, but there's an even bigger problem, right? A laser itself is kind of like a clicker, right? A laser has a wavelength, a very fixed wavelength and frequency. And as that light is coming down at a certain frequency, as the time gets compressed, that frequency gets higher. So instead of being, say, a red laser, then it becomes a blue laser, then it becomes an ultraviolet laser, then it becomes an X-ray laser, right? And now it starts not only a communication problem, but you're going to, like, it's a death ray, right? This laser beam shining down on the planet is essentially a high frequency X-ray death ray laser, right? And now you're not just worried about communication, but you're worried about destroying people, and that's all due just to the time dilation. Well, there's a simple solution: don't shine the laser. Just wait an hour, or wait 7 years, and communicate when you come back. Well, the problem here is that even if you're not shining the laser, the entire universe is essentially a laser, right? There is just light shining everywhere in the universe. What's the most pervasive light in the universe? It's what we call the cosmic microwave background radiation, right? You've probably seen pictures of like this from WMAP, Kobe, Planck, these instruments that measure this very cold 2-degree Kelvin radio emission from everywhere in the universe left over from the Big Bang. But okay, that's not such a problem. It's 2 degrees Kelvin. Well, it's 2 degrees Kelvin where it's coming from. But if we start cranking up that factor of 60,000, so here's just like a little picture as what it would look like as you get closer and closer to the black hole, right? It's kind of like a sky map. You know, the big black hole on one side as you're orbiting around it, and you see the cosmic microwave background radiation is getting distorted, and it's also going to get Doppler shifted, right? We get closer and closer, the whole sky gets squeezed up into a little point. I can't even get closer than this, or it just kind of doesn't look like anything to the human eye because this is the whole sky. But trust me, it essentially squeezes down into a single point, and it gets boosted up by that factor of 60,000. So the Doppler shift of the time dilation, the Doppler shift, and the temperature change, those are all the exact same thing. They're all different sides of the same coin. So a factor of 60,000 in time dilation corresponds directly to a factor of 60,000 in temperature. So now instead of thinking of a 2-degree Kelvin background radio flux, now we're talking 2 degrees get boosted up to like 100,000 degrees of ultraviolet X-ray light shining right on your face. So if you're a planet, now getting back to our habitable zone, it's no longer habitable, even if there's no accretion disk, just from the background radiation of the universe alone, because of that incredible time dilation, you get, oh, here, I forgot, sorry, I had that little zoom in of this point right there. You zoom in to this radius at Miller's planet's orbit, and you can see the temperature scale is getting up 100,000, close to a million degrees. So this is no good. Here is the habitable zone, again, function of radius, and now the flux. This black line is what that flux would be from the Doppler shifted CMB, and Miller's planet is somewhere up here at hundreds of thousands of watts per centimeter squared, and the habitable zone would be way out here. So even if there's no accretion, planet like Miller's planet would not be habitable just due to the blue shifted, Doppler shifted cosmic microwave background radiation. And the truth is, while I said the CMB is the leading source of energy in the entire universe, that's kind of if you average over the whole universe. But these guys aren't averaging over the whole universe. They're right in the middle of a big galaxy with stars all over the place, right? Here's another picture of what the center of our galaxy looks like. Even though the black hole in the center of our galaxy isn't particularly bright, it's surrounded by gas and stars. More of an artist impression, just like stars going everywhere. In fact, the night, if our planet were in that center of the galaxy, the night sky alone would be 100,000 times brighter than where it is, where the solar system is, just because there's so many more stars densely packed into the center of the galaxy. So if you, instead of not just thinking about the cosmic microwave background radiation, but just the stellar, ambient stellar light, this is what it would look like, right? The stellar light is about 100,000 times brighter than the CMB. So the habitable zone goes from down here way all the way out down to, now we're talking maybe only a tenth of a radius outside of the horizon. So all of these factors, when you start factoring in the real physics into the science fiction, show that there's just no way that a planet that close to to a black hole would be at all habitable. But, you know, we're talking science fiction, we're talking creativity. So maybe we can make like a giant tinfoil sphere around our planet to reflect all of this CMB and starlight. In fact, that's what a lot of sci-fi movies do. They call the Dyson sphere, where you either surround your planet or your entire star with like a giant metal shell to either keep light in or to prevent energy and light from coming inside. So we'll get rid of all the CMB, we'll get rid of all the starlight. What do we've got now? Neutrinos, right? Even if you can block out all the light, there's still neutrinos can get through anything. And there are neutrinos everywhere in the universe, both from the cosmic background, just like there's the cosmic microwaves, there are the cosmic neutrino background. And there are also neutrinos flying everywhere just from kind of ambient supernova going off all over the universe. So here I kind of had to zoom out the scale here, and coupling the neutrinos to either the atmosphere or some sort of, you can think of it like as geothermal heating, right? The neutrinos could heat up the inside of a planet to keep it warm and habitable. This is the radius at which now we're talking, you know, much closer, only a 10 to the minus 8, they're 10 to the minus 9 times the event horizon. Just outside of the black hole, you could still be habitable. You still get enough flux from the neutrinos. Yeah, so this black line is if you absorb the neutrinos in the atmosphere. The dotted line is if you absorb them in like the core to make it into geothermal heating of the planet. So that's just another way that you can make a planet either, again, kind of two sides of the coin, habitable or very, very hot, depending on how close you are to the central black hole. And then one more, looking at the time again, I'm just going to add one more kind of creative idea, because again, there's something that Mauricio mentioned. I've spent a lot of time thinking about dark matter. Right, here's just a nice movie we made of dark matter particles, which are, again, pervasive throughout the entire universe and possibly even more penetrating than neutrinos. So even if you could make a Dyson sphere that could block out all the light and all the neutrinos, you have dark matter that really just goes through everything. And then as you get closer and closer to the black hole, it kind of concentrates on these orbits around the black hole and heats up, heats up either the atmosphere through dark matter, baryon scattering, or again, in the core of the planet. You could also heat up the planet from dark matter scattering, just skipping through some of the details here, but we end up with kind of another type of figure based on different dark matter models of how to heat up a planet to habitable. And you know, I think I'm just going to show one last one because, of course, the connection to Kip Thorne is gravitational waves. I was going to skip through it a little bit quickly. As you know, from LIGO is now, well, it's not operational right now, but as we ramp up to the next observing run 04, we've seen dozens and dozens of black hole mergers. We now know that black holes merge throughout and neutron stars merge throughout the galaxy, producing these bursts of gravitational waves. Well, you can do the same exact calculation of the ambient gravitational waves coming from all over the universe. And again, here we can make kind of a habitable zone plot. This is just showing the flux of gravitational waves impinging on these planets near the black hole. But the big unknown, of course, is how do you get the energy out of the black hole? Or sorry, out of the gravitational waves. It's notoriously difficult couple matter to gravitational waves, which is why they're just so hard to detect. But a couple different kind of fanciful ideas, threw them in there. You can read that in the paper. It's not worth spending the time to get into now. And yeah, so pulling it to the end, we've discussed I guess 9 different ways that we can get energy from the universe onto a planet, most of which seem to be quite deadly. But if you tune your orbits right, instead of thinking of how they can kill you, you can think of it how they keep you warm at night and make a habitable planet around a black hole. So with that, I will show a pretty picture and open it up to questions.
So thank you so much, Jeremy. I have to say it was a really multidisciplinary talk. I mean, speaking about black hole and habitability, moving to neutrino background physics, and to dark energy, to gravitational waves, still keeping in mind the black hole and habitability. It's really very nice, amazing. Thank you so much. We have already the first. So again, you can ask your questions by raising your hand, then you will be unmute, or just write your question in the chat. And we can already unmute William Wall. William, can you hear us?
Yes, yes, I can. I hope all of you can hear me. Yeah, I don't know what to say. I mean, your talk is so good. I mean, this is something you could give to the public, or some version of it to the public. It's a great way of teaching science and getting people interested in physics and relativity. But you're quite welcome. I mean, I do have a question though. I mean, I have a couple questions. One I want to put in the chat, but one question I have is, if you can imagine having a civilization supposedly on a planet like that, assuming such a civilization could exist despite whatever problems there are, physical problems there are, they could if they sent out signals, the signals would come out so slowly we wouldn't recognize them as signals. And then, I mean, this is something for SETI to consider. Maybe, I mean, there may be signals out there that we don't recognize as signals from an intelligent civilization. So thought maybe you'd like to comment on that.
Yeah. Well, hopefully we do listen to signals at multiple wavelengths, so that I think the wavelength shouldn't be too much of a problem, whether we see it in optical or radio. But I mean, it's a good question, and I think some biologists have more intelligent things to say about this. But what's to make us think that their thought process is the same kind of speed as ours, right? If they're advanced enough, they could be, thinking like computer chips, in which case, they're having a billion coherent thoughts per second. So in which case the time dilation might actually be the only way that we could actually have a coherent conversation with them. So, it's an interesting idea to speculate on.
Yeah, that's an interesting point you've raised there. I just wanted to say that even though I like the movie Interstellar overall, at the end he leaves his daughter to go off with the female astronaut. I mean, I have children. There's no way I would do that. So that's one thing I really hated about the movie. Anyway, thank you.
So we have some question in the chat. One of them is from, let me read it. There are so many questions now. Michael Bremer. And from an Earth-like planet orbiting a supermassive black hole, what would be the radius of tidal disruption?
So tidal disruption is different than tidal locking, obviously, right? The moon is locked, but it's not disrupted. Even Mercury is kind of tidally locked to the sun, but it's not disrupted. But it's essentially the same equation that you use, and it has kind of the same scaling with mass. But it's, I don't know the number offhand. It's going to be something like somewhere between 10 to 100 times closer. So for example, and again, since it scales with masses, like if the moon was if it was 100 times closer, it would actually be in the Earth. But even 10 times closer, right, the moon would probably get disrupted at that point. So for the tidal disruption, you can kind of think of it as something like 10 times closer. Now, if that's the case, though, then I think for some of these numbers that we threw around, that would say that these planets actually would get tidally disrupted by the black hole. The problem is then is these scaling relationships actually also in the regime that we're looking at, they break down because Newton, right? They're all derived from Newtonian physics, and the gravitational potential. In some aspects, it gets very strong near the horizon, but in some aspects, it also kind of flattens out. So we kind of win and lose. So in fact, again, check it in the book. Kip has a chapter about tidal forces and explains that for the specific numbers used for Gargantua and Miller's planet, it would be tidally locked, but it would not be tidally disrupted.
Okay, so we have here one more question. Assuming the planet is surrounded by a Dyson-type spherical protection, what about the tidal force on that structure, or for that matter on the planet itself? Yeah.
So as long as your Dyson sphere is not too, I don't know exactly how to build a Dyson sphere, but as long as it's not too much bigger than the planet, then the tidal force, and it's not so massive that it itself is self-gravitating, you should probably have the same effect, the same tidal forces as you do on the planet itself. If you were to make the Dyson sphere around the entire star and the entire black hole, this actually is an interesting problem in orbital dynamics, right? Because it's very hard to make a rigid sphere orbit, right? You can make a rigid ring orbit a planet or orbit a star, but it's very hard to make a rigid sphere because everything wants to move on a great circle, and that's just impossible for a rigid sphere. So yeah, I don't know how to do it, but hopefully our future AI overlords will figure it out.
Okay, there is one question at the end, which, I am not sure. That's not
the one about the electrons and gravitational waves. Yeah, so I mean, no, it's a great question because in a normal question, the answer, or in a normal talk, the answer would just be like, no, okay, let's move on. But
well, just orbiting, we already learned that these are quantum physics. It's not just
so orbiting is in a classical sense, yes, they do. If you think of an electron as like a planet orbiting a star, a mass going in a circle, it's going to accelerate. But the quantum effects mean that the electron's not really orbiting, it's just kind of everywhere at once, which is why the electron itself doesn't emit, forget gravitational waves, really the electron should be emitting electromagnetic waves, right? Anytime you accelerate a charge in a circle, you should be radiating that away, but of course it doesn't, and which is why atoms are stable and we are all able to live. That being said, if you do want to see it as a kind of a semi-classical problem, yes, you have a mass going in a circle at close to the speed of light, it should emit some tiny amount of gravitational waves. But for the point of this talk, more important than emitting gravitational waves, it could absorb, right? Just like an antenna can emit waves and absorb waves. Let me get back to where's my, kind of skipped over very quickly at the end, right? You can have molecular vibrations at very high frequencies, right? So as you zoom in close to this black hole, the frequency, the Doppler shift gets so high that the gravitational waves get shifted from like the 1 Hertz regime up to the 10 to the 13, 10 to the 14 Hertz regime. And now you're talking molecular vibration and electronic orbital frequencies. So again, in this kind of thought experiment, not only could these electrons feel and absorb gravitational waves, but the gravitational waves might even be able to start ionizing the atoms and ripping molecules apart and using that as a source of heat. So fun stuff to think about.
So thank you once more for this beautiful talk. Now we're listening to you. Apart the great job for multidisciplinarity, I have to add one more keyword, which is creativity. I think this talk is also a beautiful example of creativity. Thank you once more, and thank you for everybody participating and listening to Jeremy Schnittman. And have a nice day in Washington and a nice evening in Europe.